Thank you for coming. I'm Alberto Escolar. I'm the guy who brought the native simulator and its predecessor and some of its integration and the tooling around in Zephyr. So today we can talk a little bit about it. So what I hope to cover today is first a very simple overview of why is it that we have the native simulator and what it is that you can actually get from using it. The second thing is going actually into much more detail about how it is that it actually works. And then coming back a little bit out into how you as a user would need, or what you would need to know as a user when using it. First, from the point of view of a basic user, and after as an advanced user, as a user that maybe wants to build his own drivers or so. So the first thing, why do we want the native simulator? So we are developing embedded software, no? And when we do this, we have some limitations just because of working with embedded devices and with hardware that can be a bit moody sometimes. So we would like to be able to test our software as much as possible in our own computers and to do it in a way that allows us to use all the tools that we have in a computer for normal, user space development in your computer. We would like to do it as fast as possible, meaning if we can run 100 times faster than real time, we certainly prefer it, so that we can run our tests fast. We would like to run with GDB or with the replay or record replay debugger. We would like to instrument our code in any way that we could possibly do. And also we would like to be able to run our code or our tests in continuous integration without the need of having actual embedded hardware, or to run as much as possible without the need to have embedded hardware to save cost and to save time. And also to be reliable so that we don't have flakiness in our CI just because of the realities of running with a lot of boards in a farm. So with this, I don't mean that we want to do unit testing. Of course, unit testing is fine, but I'm not talking about building a component with mocks around. I'm talking about building as much as possible of our embedded software, of our embedded image, and running it in our computer. And with this, I also don't mean then just building an image for QEMU that we would then just run in QEMU. What I'm talking is about actually building it for our computer as a normal program in our computer, so we can debug it like any other program. Yes, I can try to do that. Okay. I can also talk louder, but I get well. Anyway, so what we would like is our code to be deterministic wherever that is possible. So what we would like is that if we run the same test twice, we want to get the same results again and again. So if we reproduce a bug, we reproduce it all the time. We would like to run it fast. We would like to be able to debug it, as I said, and we would like to instrument it, meaning instrument it with the other sanitizer, with the undefined behavior sanitizer library, with bulk grind, or any other of the multiple tools that we have out there. And another thing that we would like to do that is a little bit contrary to the reproducibility part is that we would like to have as easy as possible access to our host to be able to test. So one thing that we would like to do is to be able to, from our embedded test code, to be able to just open a file to read input data that we feed, in our test, or to be able to just dump out the results into files. We would like to be able to use interactively our embedded code, meaning you actually use the embedded cell from our computer. We would like to be able to test connecting to real hardware and to real networks from our computer. And we would like to communicate with, in general, any tool that we have in our host or any library that we may have in our host. So here I have a few examples of the kind of things that you actually get when you build using native sim. So the first thing there is just adding a trivial bug in the kernel initialization code. So I'm just going over here an array of pointers during the initialization. And what this will do is simply, try to reference a pointer that it shouldn't try to reference. So what I'm then doing is just building it targeting native sim like you would build. You can build it with SimMake or with West. That is perfectly fine. And in this case, I'm going to enable the other sanitizer library by just using this kconfig. And then I produce an executable for my host, and I just run it. And when I run it, because I have the other sanitizer library, the sanitizer library is telling me that, okay, I'm actually trying to dereference a pointer that is pointing to something funny. It's because it's not a pointer. And it's actually pointing me to the line, and that line is just 2 lines below where I introduced the bug. Another similar example is here using the undefined behavior sanitizer. It's another library that you can build with. And in this case, the undefined behaviors do have an integer that we are going to overflow during the boot banner print, just any place. And we are also just then building, in this case, hello world. Any sample will do, because this is kernel code. And we are enabling this kconfig, and we are building, and then the undefined behavior sanitizers tell us that, okay, this is undefined behavior by the C standard. Similarly, we can use a tool like Valgrind. This is the memcheck tool from Valgrind. That is the one that you run by default. I'm just here adding another similar bug during the kernel init. This is just trying to dereference a null pointer in a printf, a silly bug. In this case, we just built without any kconfig options, because Valgrind doesn't need anything linked with it. All that we need to do then is run the executable with Valgrind. And then Valgrind is going to tell, okay, you have a segmentation fault, you are trying to dereference a null pointer, and this is the call stack where this is happening. Now, I can also then run the exact same code with the exact same bug in GDB. And in this case, you can see that I just let GDB run the code until it will trap on the seg fault, and it will just stop there, and I can see, okay, this pointer was null. I could, of course, instead of just letting the code run like this, I could have set any breakpoints I wanted, any watch points. I could have done anything I wanted, and I would have got the exact same results, just running in GDB or running without it. Another thing that you get when you are using native sim that is also quite useful is that you can use other tools like Valgrind's callgrind. This is a very nice tool that allows you to profile your code and see how you are calling what from where and how much time you're spending. So in this particular case, it's actually the Bluetooth controller code that we are looking here at. So this was just some Bluetooth sample. And here you can see for this selected function, how it is being called from an interrupt context, how many times, and how much time was spent on that. This is something that you can just do without needing to do anything more than just run your executable in Valgrind. Similarly, because we are building for our host, we can just enable coverage. This is just a kconfig option. You enable config_coverage, and you will get the coverage information dumped to disk, and then you can collate it and generate an HTML report or whatever you want to do with it. Okay, so this was a little bit of what it is, why we are doing this and what it is that you get. And now I'm going to get into the nitty-gritty details of how we are doing this. If you understand this, you can deduce everything else that comes after. And if you cannot understand it, don't worry, I will tell you after what matters. Okay, so the idea is that we want to build as much of our code as possible for our computer as an application. So let's just do that. Let's just try to build what we can. Now, the very first thing, of course, that we are going to find ourselves with is that we are building an embedded kernel. We are building Zephyr. And Zephyr expects to interact with the MCU to do context switches, to handle interrupts, and so forth. So logically, we cannot let the Zephyr kernel do that in our MCU because the Linux kernel is running there or in our processor. But the Zephyr kernel is properly layered so that there is at the bottom of it what is called the architecture layer, and this layer is dependent on the processor architecture that you are running on. So instead of running on an x86 architecture, what we are doing is replacing this layer. And when it's implementing another layer, that from the point of view of the Zephyr kernel will just look like any other architecture, but from our point of view, will be able to run on top of Linux. So what we are doing here is that each time that the Zephyr kernel says, okay, to architecture, I want to start a new thread, what we are going to do actually is start a new pthread, and we are going to immediately stop that pthread there. Then when the Zephyr kernel will say, okay, I want to swap from one thread to another, what we are going to do is pause the thread that was currently executing in a semaphore, and we are then releasing the other thread that needs to execute now. So in that way, we are implementing the context switching. Similarly, we are implementing the architecture handling or the interrupt handling inside the architecture layer. So this is, I will go a bit into details later, but whenever an interrupt comes, then we just handle it in the architecture layer. Again, from the point of view of the kernel, it looks like any other interrupt coming. Another thing that we do differently here, or a bit differently, is that we don't need to, or we don't initialize our code like we would normally initialize in a normal architecture. In a normal architecture, you would do the VSS and data initialization during the boot of the system. Here, we just let the elf loader initialize those. What we do normally, like in the Zephyr initialization, is the constructions and initialization functions for the embedded code. Those we run just like in the, during the kernel boot, because normally those functions will need the kernel to be up and running. Okay, so now that we have replaced the initialization and we have replaced the architecture layer, then you could say, okay, maybe my Linux program main should be just this. I can just call into the Zephyr early boot start, and things should work, maybe. Well, actually, they will start. The Zephyr will start initializing if you do this with these replacements. But of course, it's going to get incredibly boring, incredibly fast, because the Zephyr kernel expects interrupts from the system tick and so forth, and nothing is going to give you an interrupt if you just do this. So the kernel will run, it would go to sleep, nothing will happen. So obviously, we cannot just do this. What we need to do is that we need to implement something that will make the Zephyr kernel think that interrupts are coming. So what we are actually doing at the start of our Linux program is that we start a few very simple hardware models. These hardware models are going to, one of them is the one that just simply provides the system tick, periodically provides a tick. Another model is the interrupt controller. And this model just, when the system tick wants to raise an interrupt, it gets a function call, and then we will take care of sending that interrupt up. Now, how we do this is that from the point of view of Zephyr, or from the point of view of the whole execution, we start initializing the hardware models in one thread. Then we want to start booting the CPU. So what we do is that we post the hardware models, we spawn a new thread, and in this other thread, we effectively run something that looks very similar to that. We start executing our embedded software. Now, our embedded software will execute with the hardware models stopped, so time is actually not passing, and this is actually quite important. And we do that because it's very easy to do it, and it provides us deterministic behavior, so we don't have asynchronous races between the hardware models and the software. And then we have the software, embedded software, executing until completion, until it sleeps. When it does that, then we pause the hardware models, and we pause the software, and we let the hardware continue executing. So what we have is that only one of the two executes at a time. Only the hardware models or one of the software threads will execute at a time, and this is very much on purpose. So as I said, there is no races, and everything is simple enough. Yes. So, okay, this I have mostly said. So just one thing that is probably relevant for you if you want to know the details is that from the point of view of the hardware models scheduling, everything is actually quite simple. Hardware models simply register events in the future when they want to execute. And then there is a very simple scheduling loop that looks at which hardware model wants to run next, advance the time into that, and calls back into that hardware model. And then that hardware model does whatever it wants to do. That maybe raise an interrupt. And if it wants, it raises the interrupt, which is a call to the interrupt controller, which pauses the hardware models and releases the software thread that was sleeping. And then what happens is that because sleeping the CPU is actually an architecture layer call, as soon as we are released in the architecture layer code, we check if there was any pending interrupt that is not masked and so forth. And if so, we vector into that interrupt handler. So that actually is a valid architecture, and extremely simple MCUs would do something like that. MCUs that do not, have automatic vectoring. So we just do this, and it works fine enough for us. Okay, so this I already told you. So now, how it is that, that's from the point of view of how things actually run. Now, how is it that we build things? This is also quite important if you are building some funny code for the native simulator. In Zephyr, what we are doing is, when we build Zephyr, normally we are building an embedded image, no? And our embedded image will normally have, or will have an embedded C library, will have the kernel, application libraries, whatever. So for the native simulator, actually, we are doing something very similar. What we are actually doing is that we first start by building our embedded code with maybe some replacement drivers. That's the case when we are building for native sim, and with a replace architecture layer. And we just build, like that, a image, but we are not building a final image. What we are doing is building or pre-linking an image. We are doing what is called an incremental relocatable link. That means that we can resolve as much as we can already inside that link, and that's what we do. So everything that can be resolved in that link will be resolved, but we allow for undefined references to still exist. And that's because we are going to then later link again. And when we are doing this linking, we can already link, if we want, with an embedded C library, so that our embedded C library will be used by our embedded code. Now, that's the first step. The second step that we do is that we take that image and we hide everything that is inside that image. What we are doing in practice is that we are localizing all symbols that haven't been annotated to not be localized, and those are just literally a couple. And that couple is the one that we use to call when we boot and the one that we use to call when we raise an interrupt. Everything else is going to be hidden inside the library. It's not possible to link into it anymore. I mean, the code is there and it's runnable, but it's not going to be linkable in further steps. That's how we build the embedded side of things. Now that we have our embedded code, we are also going to build what we call the host context or the runner context. And here is where we are going to build the hardware models, is where we are going to build the part that emulates the context switching, the part that emulates stopping and starting the CPU, and the part that handles the scheduling of the hardware models and that handles the command line parsing and so forth. This part is built with the host C library because it needs to interact with the host kernel, and it's just looks very much like a normal application. And then what we do is that we link both of them together. So our runner side of things, our host side of things, is going to be able to call into those couple of symbols that I said we left, discoverable or linkable from the embedded image to boot and raise interrupts. And our embedded code is going to be actually able to call or link into anything into the runner side. So we are actually not hiding anything from the runner side, because in principle that should not be a problem. Now, another thing that is relevant to say is that when you build for native sim in Zephyr, you are only building for one embedded CPU, meaning there is only one microcontroller CPU there. But the native simulator supports actually building for many MCUs. So we have targets in Zephyr, like the 5340, which has 2 MCUs. But because we are actually building our embedded software as a pre-link library where everything is hidden, we can actually then build and link multiple of these libraries, where each of them will have a function that is called to boot it, a function that is called to raise interrupts, and then we can just link all of it together, our runner software with our embedded images, and we will have all of it together. Mind you, here, of course, when I'm talking about MCUs, I'm talking about AMP-like MCUs, meaning an MCU that has its own operating system, or maybe it's bare metal, but something that is running on its own software, its own application. I'm not talking about SMP. So meaning one operating system coordinating multiple MCUs. One thing that is also relevant to say, just as I said, only the hardware models or only an embedded thread are running one at a time. When you have n MCUs, only one of those MCUs is going to run at a time, meaning we don't have either the hardware models or the MCUs software racing each other. This means that our code can run deterministically. Okay, so now, as we are building our code in this funny way where code doesn't take time. I mean, we're just building our code to run in our computer, without any change. So nothing is when our embedded software is running, nothing is going to stop it. And because we have posted the hardware models, nothing is going to interrupt it. So how are we then going to handle a busy wait? And the answer is you cannot just busy wait, and this is the biggest limitation that you have when running in native sim. You cannot simply busy wait by having a while loop. So what we do instead is that you need to call into an architecture layer function that is this arc-busy-wait or k-busy-wait that calls into it. And what happens is that this function will actually set the CPU to sleep and will set a special timer that exists in native sim. And this special timer has an unmaskable interrupt that will wake the CPU in any case. And it's an interrupt that doesn't have an interrupt handler, so actually all that it will do is wake the CPU at the end of the busy wait, and then things will continue from there, like if nothing happened, or like if you just did a normal k-busy wait or arc-busy wait. Okay, so this was the tough part. Now we come back into the easier part. So, as I said, you cannot have just a plain busy wait. So if you have something like the code in the left, that code that is crossed out with, where you would, this is something relatively typical where you have, relatively typical when you're doing low-level embedded. You just conceptually have something that is looping forever until an interrupt handler has changed your, condition of the loop. Nothing is going to ever interrupt native sim. Because your code is just running in your computer and the hardware models are post, this will just stall everything. So instead of doing this, what you can do is either use proper synchronization primitives, meaning don't busy wait, have a semaphore, whatever it is that you want to have, or if you really want to busy wait because it's perfectly fine, maybe you're only waiting 1 microsecond or whatever, then you can do something like this or something like this. So in the first case, you can just add an if-def for this architecture that actually stops the MCU, the processor. And if you do this, then your interrupt will come, and it will actually run the interrupt handler and will wake the CPU, and the condition will change. Or you can actually add a small busy wait so that you will let time pass and things will happen. You can either do it this way, or you can use this macro which expands to exactly this. This macro just expands to it, it's nothing else. Okay, another thing that is also a quite basic thing. Because your code is running as is in your computer, and if you have a pointer that you probably will have like this, where this may be pointing to a peripheral register, and you would just try to write whatever into that peripheral register. Well, if you try to do this, things will just segfault. This is not going to be in your process memory with all likelihood, unless you have modified your, or you have mapped in your hardware models in some way this memory somewhere. This is just going to segfault. So meaning don't do this. If you are working in native sim, probably you are not trying to run directly your drivers, so you don't have this problem. But otherwise, be sure to use a pointer that points to a buffer or to a structure that represents the peripheral memory. Now, other things that are relatively basic is that there is no memory protection unit of any type or memory management unit. So we are not trying to simulate this in native sim. This is more meant to be a, application development platform and testing platform, application and libraries and so forth. There is no trust zone, that's just ARM-specific technology, and we do not support today Zephyr's user-space. So that means that from anywhere in your code, from your application, you can access anything in the kernel memory. But this is a development platform. We don't care about providing you that level of access. You are allowed to break things. More things about native sim that you may want to know as a user is that, okay, so before I was talking about the native simulator, no? And the native simulator is the tool that native sim uses. And native sim is a target that we have in Zephyr. And this target tries to be very hardware agnostic. It doesn't try to provide you any particular model of any particular hardware, something where you can run, hopefully, your application as modified as possible. So instead of providing you, real drivers for something, in native sim what we provide you is funny drivers that provide you the same API as when you will have any other driver, for your application. So for example, the entropy driver is just using the Linux random API. You have, a couple of UART drivers. One of them is connecting to a pseudo terminal. You can also connect to a standard in-out. You can have N of them. Another one is connecting to a real UART. You have also the Bluetooth usage channels driver that will provide you a Bluetooth controller that from the point of view of Zephyr looks like any other Bluetooth controller, but you can then connect to a real attached, Bluetooth device or to a virtual Bluetooth device. You also have a virtual tap device if you want to run Ethernet. You have quite many different drivers. You have a display driver that will just render into a window using the SDI library. You have quite a few backends that are dedicated for native SIM, so you have a little bit nicer behavior, so you can get things into files like CTF traces and so forth. You also have a very funny driver that is this only exists for native SIM. That is, you can build this if you have an embedded file system in your application, and it will actually fuse mount from Linux your embedded file system. So from Linux, you will have a folder where you can go and look at your folders and files in your embedded target. Okay, so this was about the native simulator and native SIM. One thing that confuses people a little bit is that we also have this other family of targets in Zephyr that are the Nordic NRF vSIM or bubble SIM targets. So as I said, a native SIM is just some very hardware agnostic target, while the NRF vSIM targets are also based in the native simulator, but instead of providing you funny drivers, they just model the Nordic hardware with enough detail that you can actually run the Nordic drivers. So when you are doing this, then what happens is that you will build in your embedded image the Nordic drivers with some very minor tweaks, but you will normally not realize about any difference, let's say, or hopefully you don't realize about any difference. So what we are doing is that we are extending the native simulator basic functionality with a sort of plugin that is the models of the hardware. And this is something that any of you can do. I mean, the native simulator is very plug and play, let's say, like you can extend it with anything you want. And then these hardware models also include models of the radio, and those models of the radio hardware then will use the bubble SIM physical layer simulation to run Bluetooth or 15.4 traffic, so you actually can run a fully simulated environment where you have multiple devices, be it Zephyr or something else, that are interacting through that properly simulated radio environment. Okay, so this was it about the basic use cases, and now we go into the more advanced ones. Now, this is more like if you are building your own drivers and so forth, or you want to talk with some funny library that you have in your host or something like that. Okay, so one thing that I said before is that when we're building our embedded code, we can build it, if we want, for the native SIM with an embedded C library. If we don't say anything when we're building Zephyr for the native SIM, and we are not building any component that needs an embedded C library, we will actually default to whatever the host C library is, which typically is glibc in Linux. We do this because many people who is using native SIM, they want to have very easy access to their host. They want that when they do open, they actually open a file or a file descriptor in their host. And when they do write, they actually write to that. If we had, by default, the embedded C library, when you call open, you would call into that embedded library and not into your host library. So you wouldn't be opening a file. You would probably not do anything. Or if you had an embedded file system, you would be opening in your embedded file system the file. But if you are building some component that needs an embedded C library, by default, we will build or allow our embedded code with picolibc. You can also choose minimal libc if you want. So that means that you need to be a bit careful when you build with native SIM about which C library you are building with and what it is that you are calling when you call into the C library, especially if you are building your own libraries or your own drivers, or you are calling into the host or want to call into the host. So what we do then for making it easy to build drivers for native SIM is that we have this funny header with the equivalent C file that you can include from your embedded code, And what this does is that it provides you a extremely easy way to call into the host C library from the embedded code. So if you want to actually malloc in the host process heap, then what you do is that you call NSI underscore host underscore malloc, and then you're calling the host C library malloc. You want to do a free, the same NSI underscore host underscore free, and that will free in the process heap. That's one way to get, into the C library from your embedded code safely, like independently of which embedded library you have. But this you can only do it if you have relatively simple things. I mean, you don't have trampolines for all kind of complex things. If you have a relatively complex driver, you may need to split your driver in two, which effectively means that you would have part of your driver built in the embedded context and part of your native SIM driver built in the host context. So literally you have two C files. One of your sites is built with the embedded library, or the embedded C library, with the Zephyr include paths, and therefore built with the bytes tree and so forth, like anything else, while the host site doesn't see anything from Zephyr, it only sees Linux, the host C library. So if you do this, then you have your host side of your driver doing any interaction with the host, and your embedded side of the driver calling into your host side of the driver to interact with it. Remember that, as we said, everything in the host build is linkable directly from the embedded side. So you can just call directly, and you will be able to link into your host side of the driver without any problem. You cannot do the same in the other direction. From the host side, you cannot link into your embedded side directly. You can use callbacks if you want, or you can use a funny macro, that is this macro, or set of macros, to annotate any embedded symbol so that it will be visible in the later link. The only thing that you need to be careful with this is if you have multiple embedded images, because then, if you have that driver built in all the images, they will conflict during link time. Now, another thing that you need to be careful when building your split drivers is that you are building very likely with different C libraries in either side. And that means that you should not pass from one side to the other of your driver anything that depends on types that are defined by the C library itself. So you can use basic types defined by the compiler, meaning int, long, char, and so forth. Those types will be the same. But any type that is defined by the C library, in principle, is going to be different. Meaning, whatever more complex API that you want to have, whatever structure that you want to pass or complex type that you want to have, simply define it in your own header, have that header not include Zephyr headers and so forth, because the host will not see them, and just include that header from both sides of your driver. And in that way, you will just have something that is the same. You can also, of course, use standard int types if you are happy with that. But you cannot use something like struct socket, because struct socket is going to be very different in Zephyr than in Linux. Another thing that you need to be aware of is that error numbers returned by the C library are going to be different in each side, because there are different C libraries. So if you want to pass an error number from one side of your driver to the other, you have this small header that allows you to convert error numbers so that, when you use them in the embedded side of things, they are actually coherent with your embedded C library view. Okay, so this I told you already. So another thing that is then important is to be careful with threading. You can spawn from the host side Linux pthreads if you want. But if you do that, remember that now you have an asynchronous pthread running with your code, and that asynchronous pthread is going to run ahead, meaning it is your responsibility to synchronize it with everything else. You need to be aware that if you do any kind of call into the host that is blocking from non-asynchronous thread, you are going to block everything. Remember that, as we said, our hardware models or our embedded code, only one of them is running at a time, and everything is waiting for that. So if you do a blocking read, everything is blocked. That may be perfectly fine if you actually wanted to block your execution until something happens. But maybe that's not what you want. So just remember it and be careful. Another thing that you need to be careful is to not call from asynchronous host threads embedded code because you are going to completely mess up the state of the Zephyr kernel. Similarly, do not call from hardware models threads the Zephyr embedded code. Again, the embedded CPU or Zephyr thinks is sleeping. If you start calling from there into Zephyr code, you are going to corrupt this state in no time. The kernel is going to crash very badly. So, actually, that was everything I wanted to tell you. If you want more information, you have these nice links. You have the PDF already online. And otherwise, you are more than welcome to ask any questions. So, I think Carles raised first, then Jordan.
What's the config option to select the library?
Just the library name, so config_picolibc equals yes. So
Select whether you use the host or the. Oh, it's the same. It's the same config choice.
It's the same choice, yes. So you select config_ native libc, I think, and then you select that one. Yes.
Why are the errors different between the libraries?
Why are what? Sorry.
Error codes different between...
Because okay, so the question, sorry, I need to repeat questions. The question is, why are the error numbers different between C libraries? And just because the C library can do whatever it wants, so they don't need to agree between each other. Yes?
The question is about writing your own drivers for native sim, and specifically, an example, UART driver. If it wants to get some data from the host side, normally you would call something like read on Linux, and that would be a blocking call. Or you can do read non-block, but then it will return immediately if there is no data. So how is this actually handled in native sim when you don't know when the data will arrive? Do we just do polling, like non-blocking polling, every time you wake up the hardware model?
Yes, okay. So the question is, how do we then handle native sim drivers where we want to poll for data or get data out and we don't know if the data is there or not, if we just, we do not block, if we just poll all the time. And the answer is that in the drivers that we have, we are actually just polling. It is a extremely simple mechanism. We just check if there is something. If there is nothing, we wait 10 milliseconds or so and check again. It is conceptually simple.
You're saying that's the virtual simulated time, right?
Correct.
So you just set like 10 millisecond delay between those hardware events in native sim.
Well, in this case, because we're doing it at the driver level, it's not even a hardware event. It's actually a driver in Zephyr that is polling on its own. So you don't even need, for something like that, actually many of the drivers for native sim, they don't have any hardware models behind. They're just interacting directly with, the Linux kernel.
Through the trampolines that you described.
Yes, some of them using trampolines and some of them split in the driver. There is both things.
One of your first slides, you said don't use it for unit testing.
Okay, so the question is if we cannot use this for unit testing. No, okay, so what I meant is this is not unit testing. My target was not to run unit test. We already can do that. We already have tools in Zephyr to run unit test. You can, if you want, run something that is very much akin to unit test, but you are going to build it with the Zephyr kernel. So it is not anymore unit test. Well, you don't need to mock the kernel if you wish. But you can run something that would be akin to unit test, but this is not just,
More application level, not dependent. So I would like to run my unit test suite and use a coverage, and I thought the native sim would be nice.
Yeah, you can certainly do that. So you can run something that is similar to unit tests in here. You can run something that is similar to partial integration test. You can run something that is similar to full integration test. And actually quite many of the tests that we have in Zephyr, in CI, for many of our components are running in native sim instead of bothering mocking things. So if you are using the kernel in some kind of meaningful way, mocking it starts to become a pain. So you just run with the kernel, build with the kernel, and use it. Yes?
If the Zephyr threads are backed by p-threads underneath the hood, are you setting the p-thread stack size, and are you doing things like detecting below your stack and then surfacing it like you would running on hardware?
Okay, so the question is, given that we are using p-threads underlying for the Zephyr threads, do we bother, let's say, with the stack? And the answer is, we just don't bother with the stack. We actually use the pthread stack directly. You may have seen that there is a kconfig option for native sim or for the native simulator builds that sets a preferred default stack size that is extremely small. That's because we only keep in the embedded thread stack a little bit of metadata to know the parameters for the thread and so forth. We just, the default pthread stack is huge, is going to fit there. So you just, I mean, if you happen to actually have an infinite recursion, you are going to anyway fault, and just your, normal C library fault handling will handle it. Welcome. Any more questions? Please.
Maybe a simple question. There is a native sim /native/32, and native sim/native/64.
Correct.
Could you please explain what are these three variants?
Okay, so the question is, why do we have native sim and native sim 64? So actually, we just have two targets. We have native sim, the 32-bit version, and the 64-bit version. It's just that by default, the default variant is the 32-bit version. So that's why if you only write native sim, you don't need to write /native/32. So the reason why we have these two targets is because even though the Zephyr kernel for quite many years is 64-bit compatible, a lot of our application code is not. A lot of our application and library code is not. So we actually need to provide means for people to be able to develop and debug that code that will just fail horribly if you try to build it using 64-bit pointer sizes. Also, being able to build as 32 bits with 32-bit pointers is kind of nice when you are targeting a 32-bit embedded target, because your structure sizes will be much more coherent with the embedded sizes. So you will see some bugs that may be actually hidden, or vice versa, if you are building as a 64-bit target. Maybe your structure suddenly will get padded much bigger, or there will be, things will be quite different, and some bugs you may not see if you build with 64. So those two reasons means that we need to have a 32-bit target. And if you cannot, for some reason, build for 32-bit binaries, then just build for the 64. If you're unlucky enough that the code you're trying to test is not 32-bit compatible, well, I cannot do anything for you.
Hardware models is not right. Hardware models require.
Hold on. He asked for native sim.
Okay.
Now, if we are talking about the NRF bsim targets, there we need to actually build as 32 bits. And that's because the hardware models model hardware where the hardware stores pointers in registers, and those registers are 32 bits because the platform is a Cortex-M33 with 32-bit pointers. So if we suddenly had 64-bit pointers, we couldn't store them in the hardware, and the DMA of the hardware couldn't go read from our memory. But that is for the NRF bsim targets, not for native sim. Johan first, sorry.
What's the main obstacle or reason why we don't have this for macOS?
There is several things. Okay, so the question is, why does this not work for macOS? So there is several things. One of them is that, and probably, maybe the parameter, okay, there is several, but all of them are important. The one very important one is that when we are actually building for native sim, we are building very, very similarly to how we build for the embedded target. We're actually using ELFs as intermediate steps. We are looking into those, we are doing several link steps. Some of them are kind of wasteful just so that we can look into the output and generate headers based on that output and so forth. And all our build process, all our tooling is based on ELF. Linux, luckily, uses ELF also. So we can then just use all our build practically the same for native sim as we do, for embedded targets. If you have an operating system that doesn't use ELF, then we need to change all our build system to be able to look into whatever, binary executable format to be able to look into what sections are there and so forth. That's one issue. Then there's other issues with, macOS not really being as, POSIX compliant as they claim. So even that the basics of native sim try to just be plain POSIX compliant, there's most likely than not going to be problems. There is another issue that would be more minor, that is that quite a few of the drivers that I showed before, like certainly the Fuse driver or quite many of those drivers, that are extremely Linux specific. So you are not going to have any of those drivers for Mac. So that's simply where we are. I work in Linux. I've made it work for Linux. You want to make it work in Mac? Go ahead.
What about Windows?
Same thing, running WSL. It's a virtual machine, you can run there.
Is that as problematic as macOS, or is that less?
I would expect that there is going to be very similar constraints because, again, the binary format is different and our build spells and everything else that I said is going to probably have the same kind of constraints. Jaco?
So if we use native sims for integration testing, like our CI stuff, is there a way to detect stack overflows in CI with native sim?
Okay, so the question is there a way to detect stack overflows in CI with native sim? Okay, so if your stack overflow is...
Would have occurred on the actual target? If the stack overflow would have occurred was running on actual hardware?
Probably not. So if your stack is just a couple of bytes short because we are just using a massive pthread stack, you are not going to see this. But the thing here is that you need to be aware that even if you would have we could have actually set the pthread to use the statically allocated embedded stack. But the thing is, because your call stack in native sim is going to be different because there's more architecture layer calls, things are not, your stack is not going to be the same anyhow. So you will need to have a different size of the stack in native sim than you would have had in your embedded target. So if you were 2 bytes off, no. You wouldn't, even if we did that, you were not going to find it. You would just have a lot of pain because then you would also need to bother about configuring a proper stack for native sim that is going to be different than the proper stack for your embedded target.